In this video, we're going to see another example of computing the inverse Laplace transform of a function. In this case, we're going to have to use the algebraic trick of partial fractions to take this thing that we're trying to compute the inverse Laplace transform of and to write it in a way that is compatible with our knowledge of current Laplace transforms. We want to make this look like something that we know how to take the inverse Laplace transform of. So here's how this method of partial fractions is going to work out. Before I even take the inverse Laplace transform, I'm going to get rid of all of that nonsense, and I'm just going to do algebra just on the inside. Here's how it's going to work. First, I want to look down here in the denominator where I'll note that I actually have two different factors. One of them is this factor s plus 3, which is a linear and only appears once, and the other is another linear factor, s minus 1, but it is now repeated. So the method of partial fraction says, can I write this as a guess of a constant a, and then I divide out by the s minus 1, but now I just put s minus 1 to the power of 1. And because it's repeated, I do this a second time, a second constant that I call now b, but now I divide it by s minus 1 squared, and that's sufficient. It's repeated twice, so I divide out first by s minus 1 and then by s minus 1 squared. And then I have a final constant c to deal with the s plus 3 term. The next thing I'm going to do is I want to get rid of all these denominators. They're sort of messing up the work. So I'm going to multiply through by the denominator of the left-hand side. So what that's going to give me is on the left, after I get rid of the denominator, just the s squared plus the 9s plus the 2. And then on the right-hand side, first I will have an a, and so I have one s minus 1 on the bottom. So when I multiply by s minus 1 squared, that leaves me with just one s minus 1 on the top. Then I multiply by another s plus 3. Then for the b term, okay, the s minus 1 squared cancels away, and then I just multiply by an s plus 3. And then for the c term, well, the s plus 3 cancels, and so I'm just left with an s minus 1 squared. Now at this stage in a partial fraction computation, there's usually actually multiple different ways to approach it. One would be I could try to expand this all out, and then I could write out three different equations, one for the coefficients of 1, one for the coefficients of s, and one for the coefficients of s squared. The other approach that I can take is just plugging in some special values of s, and that's going to simplify things considerably. So for example, if I come here and plug in s equal to the value of 1, well, on the left-hand side, I get 1 plus 9 plus 2, which is going to be equal to 12. On the right-hand side, well, because there's an s minus 1 on the a term, that goes away. Same for the c term. If you plug in 1, that's going to go away. So all that's left is the b term. So it's a b multiplied by 1 plus 3, which is 4, and that's going to tell me that my b is equal to the value of 3. I have one of my three coefficients right off the bat. The other special value I could plug in is s equal to minus 3. If I do that on the left-hand side, I'm going to get minus 3 squared, which is going to be 9. I'm going to subtract off my 27, which is going to give me minus 18, and then plus 2 is going to give me minus 16. Then the a term is going to go away, the b term is going to go away, so I just have the c term. Minus 3 minus 1 is minus 4. I square that, I'm going to get 16, so this is going to give me a 16c, and that's going to imply that c is equal to minus 1. Another coefficient has been figured out very easily just by plugging in a special value. The last one, there's no natural remaining special values to plug in, so I'll just sort of choose something that might make it easy to compute. How about just plugging in s equal to 0? I could plug in other values, but this one's going to be easy. On the left-hand side, 0 plus 9, 0 plus 2 just gives me a 2. For my a term, this is going to give me a, and then it's going to be multiplied by a minus 1 times a 3, so multiplied by a minus 3. For the b term, I'm going to remind us that b was equal to 3, so I multiply that times 0 plus 3, so that's going to give me a plus 9. And then for the c term, we decided that c was minus 1, and then multiplied by minus 1 squared is going to give me a minus 1. So in other words, I have an 8 on the right-hand side. If I subtract that over, I'm going to have a minus 6 is a times minus 3. And so as a result, a is just equal to 2, and I have my third coefficient. We had began up here on the top where I had this expression, and I rewrote this as an a, b, and a c divided by these different denominators. And now my goal is to compute the inverse Laplace transform of this now converted right-hand side. That is, I am aiming to compute the inverse Laplace transform, and I'll write down now the whole left-hand side here. So this is 2 divided by s minus 1, plus b was 3 divided by s minus 1 squared. And then finally, the c is going to be a minus 1 divided by s plus 3. Okay, so let's move this up to give myself a little bit more space. To solve these, I'm going to remind you that the Laplace transform of t to the n was computed out to be n factorial divided out by s to the n plus 1. That's one property that we're going to use extensively. And then the other property was that the Laplace transform of e to the at times, well, some function that we knew as Laplace transform of, that this was nothing but the Laplace transform of that function, the big F, but evaluated s minus a. So knowing those two facts that we've talked about previously, I should be able to get all three of these. For example, let me look at the first expression. There's a 2 on the top, and for the 2 on the top, because of linearity, I'll just bring it out the front and ignore it. Then there's a 1 over s minus 1. That really looks like this t to the n business in the case where n was just 0. In that case, it would just be a 1 divided out by s. But it's not 1 divided by s alone, it's 1 divided by s minus 1, which happens when you have a shift down here and you have a equal to 1. So putting those two facts together, this is just going to be e to the t. Indeed, one of our very first examples of computing the Laplace transform was just e to the at. And we saw that the Laplace transform of e to the at was 1 over s minus a. So that's indeed exactly compatible even if you wanted to skip these two facts. However, we do want to use these two facts for the second example. I again have a plus 3, and I'll just pull that out because of linearity. But in the denominator, I have now an s minus 1 squared. There's two things going on. The first is that there's something squared, which looks a little bit like the Laplace transform of t to the n, where n was equal to 1. That would result in something to the 1 plus 1, or squared on the bottom. And then likewise, it's being shifted because it's not just an s squared on the bottom, it's an s minus 1 squared. So putting those two facts together, the shift portion gives the e to the t as before. And the fact that it is 1 over something squared means that I've got just a factor of t appearing, so I'm going to multiply this by a t. For the third factor, I'm going to subtract off because I've got this minus 1, and then likewise, it's just going to be an e to the minus 3t. It's the exponential shifted with a equal to minus 3. And so that is now my final answer. So the idea in this example, and indeed for many of these examples, is that you have some rational function you're trying to find the inverse Laplace transform to. You apply some algebra. In previous videos, we've seen that algebra might be completing the square. In this example, we were doing partial fractions. And when we used that algebra, we were able to write the answer as a linear combination of things that we knew the inverse Laplace transform of. Because of the elementary Laplace transform, for example, for a polynomial t to the n and this combined factor of translations, we're able to say that this expression that we got was something we knew how to compute the Laplace transform of, and thus doing the algebra of partial fractions was a big benefit to us.